Hi everyone. Today I present ViKIENet towards efficient 3D object detection with virtual key instance enhanced network. I'm from Nanyang Technological University, Singapore. Let me start with the background. 3D object detection is critical for autonomous driving, robotics, and intelligent systems. LiDAR-based detection provides accurate depth but suffers from two main issues. First, sparse point clouds, especially for distant or small objects. Second, limited semantic information. RGB images offer rich semantic content and dense structure, but lack depth information. Now, existing virtual point-based fusion methods face three key challenges. First, high computational cost. Second, noisy depth completion. Third, insufficient semantic utilization. Recent methods alleviate these challenges by converting RGB images into virtual points via depth completion to be fused with LiDAR points. Although these methods have shown outstanding results, they often introduce significant computation overhead due to the high density of virtual points and noise due to inaccurate depth completion. Besides, they do not thoroughly leverage semantic information from images. We propose the Virtual Key Instance Enhanced Network, ViKIENet, a highly efficient and effective multimodal feature fusion framework that fuses the features of virtual key instances and LiDAR points through multiple stages. Our contributions include three main components: semantic key instance selection, virtual instance focused fusion, and virtual instance to real attention. We also propose the extended version ViKIENet R with VIFFR, which includes rotationally equivariant features. SKIs, semantic key instance selection. The SKIs module generates semantically enriched VKIs to reduce the computational load associated with dense virtual points while leveraging their semantic information. A depth completion model is applied to get a corresponding depth map of the input image, and a semantic segmentation model is applied to obtain the semantic class and score of each pixel of the same image. The pixels of key instances are then converted into virtual points in the 3D space. Similar to point painting, the semantic scores are appended to these virtual points, forming VKIs which also encapsulate rich semantic information from images. Our approach addressed a problem in point painting where no corresponding LiDAR points can be found to paint on. VIFF, Virtual Instance Focused Fusion. The proposed VIFF module comprises two aspects of the fusion strategies: BEV feature fusion and ROI feature fusion. They are designed to fuse the features of VKIs with those of LiDAR points across multiple dimensions. VIFF employs a thorough and effective fusion approach within the BEV space, enhancing features and highlighting the key regions at both channel and spatial levels. For BEV feature fusion, after the BEV features are concatenated, a channel attention mechanism is applied to determine the importance of each channel. With this, a VKI spatial attention is applied to emphasize the important regions within the BEV features. For ROI feature fusion, self-attention is applied to both LiDAR and VKI ROI features. We next employed a bidirectional cross-attention between them. This configuration enables the ROI features from VKIs and the ROI features from LiDAR to learn from and complement each other. The VKI features can learn their contextual information from LiDAR features and disregard noises within themselves, while the LiDAR features can learn the semantic and denser structural information from the VKI features. VIRA, Virtual to Real Attention. To mitigate the impact of inaccurate depth information of VKIs in the fusion process, we propose the Virtual Instance to Real Attention module for preparatory 3D feature adjustments. We leverage the precise depth measurements from the associated LiDAR points to refine the raw noisy features of the VKIs. This is achieved via a cross-attention mechanism between the two feature modalities, which, in turn, produces more accurate and reliable feature representations of the VKIs. We utilize the voxel indices of the sparse 3D features from both modalities to project their coordinates onto a shared 2D camera image domain using a projection function. For each VKI feature, we resort to its 2D location in the image to identify the corresponding LiDAR features based on spatial alignment in the image domain. ViKIENet R, Rotational Transformation Equivariant VKI Features. ViKIENet R applies 2N rotational transformations to the VKIs and LiDAR points, generating multi-view feature representations. Subsequently, voxel features for each transformed point set are extracted through a transformation equivariant sparse convolutional encoder, obtaining two n sets of features. Since we only used 10% of the virtual points compared to methods using all virtual points, the computational complexity is substantially reduced, thus enabling rotation transformation equivariant networks to be applied in more resource-constrained applications. Experimental results. We evaluate our proposed ViKIEnet on the KITTI dataset, the new scenes dataset, and the JRDB dataset. On the KITTI dataset, ViKIEnet and ViKIEnet-R operate at high frame rates while achieving significant improvements in detection performance compared to existing works. Experiment results show that ViKIEnet and ViKIEnet-R achieve significant improvements in detection performance on the KITTI, JRDB, and new scenes datasets compared to existing works. As of CVPR submission, ViKIEnet ranks first on the car detection and orientation estimation leaderboard, while ViKIEnet-R ranks second on the 3D car detection leaderboard. Our ablation study shows that each fusion method brings meaningful improvements. The BEV feature fusion method brings improvement over the baseline. The ROI feature fusion method brings significant improvement. With the proposed VIRA module applied on top of VIFF, the detection performance can be further improved. Results show that each module contributes significantly, with the complete system achieving the best performance.